In today's lesson, we are going to multiply matrices together. As our example, starting off, we have a teacher assigns grades based on a weighted system. Students are graded on unit assessments, a semester project, and the final exam, each with a different weight. The matrices given below represent the weights of each kind of work and the grades for two students. We have Oscar and we have Reagan. So on the left is how the teacher weights those units, the unit assessment, project, and final. So it looks like 50%, 30%, and 20%. And on the right, matrix G is for Oscar and Reagan with those grades for the unit assessment, project, and final. So what would be the final grades for each student? So we're going to multiply the grades with those weights. To find each student's final grade, multiply the elements from that 1 by 3 matrix, the weighting. This is a 1 by 3 with 1 row and 3 columns, with the elements in the 3 by 1 matrix with the grades. That's 3 rows and 1 column. So you can see it written out here for Oscar. We took the weighted matrix, the 50%, 30%, 20%, and we're multiplying it with his grades. That column from up in matrix G, his 90, 95, and 75. To do matrix multiplication, we're going to take each element and multiply it. So the 50% for the unit assessment times 90. Then we're going to add, as we multiply the next element, the 30% with 95, and add it with the last element, 20% times 75. So all of that's been written out for you. If we type that in our calculator, we will find Oscar's final grade. So we have 50%, or the 0.50 times 90, plus 0.30 times 95, plus 0.20 times 75. Gives us 88.5 would be Oscar's final grade. Let's look now at Reagan. So we're going to do the same thing. Multiply the weight matrix by the grade matrix. That has all been written out there. Here's the weight and here is the grade matrix. Multiply each element. So the 50% times 80 plus 30% times the 70 plus the 20% times the 85. So let's grab the calculator and see what Reagan's grade would be. Reagan's grade, the 50% times 80 for the unit assessment plus 30% times 70 plus 20% times 85. Reagan's grade would be a 78. So let's take those results and let's represent them in a matrix F for final grades. So we're going to call matrix F after the multiplication of the weights times the grades. Again, that is written all out here. The weighted categories times Reagan and Oscar's grades. The answer would be a matrix of 88.5 and 78. Notice this is a 1 by 2 matrix. So in general, your rule of thumb, how matrix multiplication works, if you have the product of matrix A and B, it will have the same number of rows as A. It'll have the same number of columns as B. So let's look at this another way. If matrix A has rows and columns, and then matrix B has rows and columns, the result, the product A and B, is going to be what I underlined in pink, the rows and the columns. It's almost as though those center ones are going to cancel each other out. Now they have to be the same. If the number of columns in that first matrix does not match the number of rows in the second matrix, then the answer does not exist. We can't compute it. So those center ones do have to be the same. Let's go back and look at our example. The weight matrix was a 1 by 3. The grade matrix was a 3 by 2. The threes cancel each other out. And what was our result or our product? A 1 by 2 matrix. So when we're multiplying, remember the number of columns has to be the same as the rows in the next one that we're multiplying, or the answer wouldn't exist. Okay, let's try a couple on our own. Find the product of the two matrices. Number one, this is a 2 by 2 times a 2 by 2. So our answer is going to be what? A 2 by 2 matrix. Now we are going to multiply just like we did above. Now, the one above, the weighted matrix was only one row. So we are going to do the same thing. We're going to start off with row by column. So that's the first one I'm going to multiply. We're going to do -3 times -1 plus 4 times -1. So I did first element in the first matrix in the first row times the first element in the second matrix in the first column. Okay, we're doing row by column. When we multiply that out, I'm going to get +3 and -4. I get -1. That's going to be the first element in my matrix. We're going to multiply all this out, and then I'll write our matrix all together. We're still going to continue with the first row. Now we're going to do the second column. -3 times +1 plus 4 times 0 gives us -3, would be our next element in our matrix. Moving on to our next row, we're going to go 2 times -1 plus 2 times -1 gives us -4. Still with that second row, now second column, 2 times 1 plus 2 times 0 will give us 2. So our final answer, we got -1, first row, first column. We got -3, first row, second column goes over here. Then we got -4 and 2. Final answer. So a little tricky. Take your time and practice. Let's try number 2. First row, first column. 5 times 1 plus -3 times 0 gives us 5. Do the next column. We have 5 times 1 plus -3 times 3 gives us -4. Moving down to our next row. Rows always come first, okay? So second row, first column. 5 times 1 plus -1 times 0. Gonna have 5 there. Move to the next column. We have 5 times 1 plus -1 times 3. Gives us 2. Again, this was a 2 by 2 matrix. I'll write this out. The number of columns was the same as rows in the second, so those cancel out. Our final answer would be a 2 by 2. We have 5, -4, 5, and 2. And I'm just writing that in the order that we got them. So we did the first row, first column gives us the first element in the top left corner. The first row, second column gives me the first row, second number in our matrix, okay? On the second page of our notes, we're going to look at an augmented matrix. So remember, a matrix helps you just organize numbers or allows you to keep track of your coefficients and constants in a system of equations. So kind of a throwback to content that we've covered before without writing all those variables. So an augmented matrix shows all the coefficients and constants from a system of equations. There's a dotted line that separates the variable terms from the constant terms. You're actually going to see a dash or a dotted line that's a little bit longer. I just couldn't format it here on our notes to that full dotted line. But look at my example here. We have the system of equations. This is just 2 variables, 2 equations, but we've worked with 3 variable, 3 equations. We can do the same thing. In fact, number 4, I've got an example there. 2x plus 3y equals 1. Look how it's written in the matrix. 2 and the 3, the dotted line, and then equal to 1. Bottom equation, 2x minus 4x minus 2y equals 10. And we see those coefficients and those constants written there in that augmented matrix. So one of your standards is to take a system and represent it or recognize it written in an augmented matrix. So this is super easy. To use a matrix to represent your linear system of equations, the equations must be written in standard form first. So look at our examples. They're a little messy. So we want to make sure our x and our y are on the left side and our constants on the other. So let's start with this top equation. We need to rewrite it into standard form. So instead of 5y equals negative 3x, let's add that 3x over to the other side so that our new standard form linear system here is going to be 3x plus 5y equals 0. That's going to be my new equation I'm going to use for my matrix. Let's talk about the other equation. We've got negative 3x equals 4 plus 2y. I need the x and the y on the left, so let's subtract 2y to the other side. We have negative 3x minus 2y equals 4. We do want to leave that constant on that other side. So now that they're in standard form, let's build that augmented matrix. I'm going to list my coefficients, 3. This is the top equation that we rewrote in standard form. I've got 3, I've got 5. We'll have a dashed line and then my equal to my constant, which was 0. For the second equation, we have negative 3, negative 2, and 4. Pretty simple, huh? Now, if you happen to be asked to solve an augmented matrix, remember we solved systems on the calculator. So let's grab the calculator and let me just remind you of those steps if you happen to be asked to solve an augmented matrix, which is just a system. So on your calculator page, we go to Menu, Algebra, Solve System of Linear Equations. It does have to be all linear here, and that's what we're using to write these augmented matrices. For this example, number 3, there was only 2 equations, so we're going to leave it at 2. I'm going to use tab to get me down to OK, and we get those 2 boxes to type in our system. The top equation we had was 3x plus 5y equaled 0. Arrowing down, I'm going to put in negative 3x minus 2y equaled 4, and you hit enter, and there's your solution. Not even concerned that they're fractions at all. So let's do number 4. Number 4 is 3 equations, 3 variables. We have x, y, and z. We want to do the same thing, move all of our variable terms to the left side, and we do want them in alphabetical order, x, y, and z. Constants on the right. So let's do the top equation is not set up. It's almost, I could just flip it over pretty much. So let's see, if I add 3z, if I add 3y, if I add x all to the other side of my equal sign, we would have my x first plus the y, 3y, plus 3z equaled 0. If I added 0, subtracted 0 to the other side, it's still going to be 0. So there's our top equation. The next one, negative 9z equaled negative 5y plus 8. We would need to add the 5y to the other side. Notice there's not an x term. No big deal, okay? So I'm going to write 0x just to remind me later when I'm building my matrix. 0x plus the y, 5y, minus 9z equaled positive 8. That's my standard form equation. And last one, 5y plus 6x equals 8. I'm just going to rearrange it. And again, we don't have a z, so I'm going to put in a 0 placeholder. So 6x plus 5y plus 0z equals 8 is our standard form. So let's build that matrix. We're going to list our x, y, z, and then our dashed line with our constant. So we had 1x, 3y, 3z, dash, 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 equal to 0. In the next equation, we had 0, 5, negative 9, 8. And in our last one, we had 6, 5, 0, equal to 8. There's my augmented matrix to represent number 4. So it just needs to be rewritten in standard form, and then you just plop it in. Pretty simple, right? So I think that standard is going to be really easy on your benchmarks or your end of course. Again, if you have to solve, you just go back to the calculator and you can type it into a solve system and type in your equations. Of course, it doesn't have to be in standard form. You could type it the way we see it on number 4. So there's matrix multiplication. We actually multiplied 2 matrices together. When you're multiplying, the columns from the first one and the rows in the second one have to be the same number so that they kind of essentially cancel out, like we did with the weighting and the final grades. It was a 1 by 3 times a 3 by 2, and our result was a 1 by 2. When you actually are multiplying by hand, take your time, row by column, row by column, okay? And then augmented matrix, pretty simple concept, all right? So make sure you just change those into standard form before you plop them into your matrix. Guys, let me know if you have any questions. I'll see you in class. Have a great day.